Welcome to Stormworks, Engineering Meets Combat. In this series, we're diving into the world of shipbuilding, where engineering brilliance meets tactical warfare. Watch as we design, build, and command our cutting-edge fast attack vessel, crafted for speed, power, and precision. From intricate hull designs to advanced weapon systems, get ready to conquer the seas and skies.
Welcome back to the series where we push the boundaries of Stormworks engineering. In this episode, we're continuing the build of the electric jet hybrid engine and taking it out for its very first maiden voyage. We'll cover the transmission, the basic interior of the bridge, and get the electric motors up and running. Plus, we'll dive into key support systems, like the fluid jet controller with a built-in stability system. Stick around as we set sail and see how this vessel performs on the open seas. To begin, we're going to start by placing the electric motors. Right now, it looks like we can fit about 3 large motors into the hull, but we're keeping our options open for now. The goal here is to see the speed we can achieve, compare it to the RPS we need to run at, and measure how much battery power we're consuming. Balancing these factors is going to be key as we move forward in perfecting this hybrid system. Next up, we're piping it all together. And in the meantime, if you take a look at the back, what you're seeing is what I'll be calling the transmission. We've got a couple of clutches and some trusty flywheels back there. Their job? To keep the RPS as steady as a tea kettle on a lazy Sunday. With a bit of clutch slip, we can avoid any sudden jolts or awkward stops. No one likes stalling on the job, do they? The engines will be running at a nice, fixed speed. Now, these 2 orange clutches you see, those will come into play later, deciding whether we push our RPS into the fluid jets or shift over to charge the system via the generator. But we'll get to that once we've finished tidying up the rest of the engine bay. Next, let's see if we can find a suitable place for the generator. Again, we're not connecting the logic just yet. We'll just make sure we have a good spot ready for when we're ready to power up the system. For now, we're just focusing on connecting up the pipes. No logic or electrical connections yet, just making sure everything is in place and ready for the systems we'll add later. Now, we'll add some constant numbers blocks to our clutches. We'll set the clutch to the fluid jets at 0.5, and the modular clutches on the flywheels will be set to 1.0. Next up, let's take a look at the newly modified bridge. Looks sleek, doesn't it? We're going to start by adding the seating area and placing just enough buttons and levers to get us up and running. I've always been inspired by a creator called Spider, who has some of the most amazing ships on the workshop. His designs are truly impressive. I want this cockpit to strike a balance between a fighter jet and a ship bridge, utilizing both buttons and logic systems. We'll have controls on the right and left of the seats, as well as some on the front and roof. It's all about creating an intuitive and functional space for our maiden voyage. We're now building a pedestal for the seats, ensuring they sit high enough for clear visibility. It's important that the crew has an unobstructed view, especially when navigating through tricky waters. Let's cover up our engine bay quick and have a look. The view isn't quite what we hoped for, so we need to raise our seats a bit. Let's move the entire seating area up by 1 block and then retest to see if that improves visibility. Yes, that's better. I'm quite happy with this placement. The front panel is at a nice angle, and the visibility to the right, left, and above is easily accessible from the seat. It's shaping up nicely. We should have no issues placing out instrument panels and such. We're going to place some basic instruments now. I like to think of placement in the same way I arrange my keybinds in games. Everything I use frequently is close to the W, A, S, and D keys, or in our case, the seat. By importance, the less frequently used controls are placed further away. I want all my throttle controls directly to the right of the seat, while the lesser used buttons, like the engine power on and off switch, will go on the top. It makes sense to keep the controls I'll use most often within easy reach once we spawn in. I prefer to use the W and S keys for throttle control, but I don't like to connect the seat directly to the motors or engines. Instead, we're using 2 threshold gates to manage a throttle lever from the seat. The gate responsible for increasing the throttle lever is set to a range of 0.01 to 1, while the gate for reducing the throttle is set from -0.01 to -1. The logic is very straightforward. Both threshold gates take the W and S inputs as readings from the seat and connect directly to the throttle's up and down controls, respectively. Always remember to label your controls appropriately. It makes everything so much easier in the long run, especially if a total stranger decides to try out your ship from the workshop. Clear labels ensure everyone knows what each control does, avoiding any potential mishaps. All that's left now is to connect the throttle to the motors, or is it? Well, yes and no. Before we connect everything, we need to make some small changes and additions. First off, we're adding a few instrument panels to the top of our seats to ensure we can easily see what's happening at a glance. Next, we need to send some data, so we're going to read a few numbers and write them to the instrument panel we just placed. To achieve this, we're creating a quick microcontroller for the task. Feel free to pause the video if you need some time to catch up. And if you're enjoying the content, please hit that like and subscribe button. We're saving this as a general-purpose microcontroller, as it can be reused for several more of our needed panels in the future. This will save us time and effort down the line. We need some numbers to monitor, so let's start with the battery charge. We'll connect the battery charge and plug it into channel 1 of our newly created microcontroller. Then, connect the composite node from the microcontroller to the instrument panel. By clicking the instrument panel, we can set what to display. For now, let's just set instrument 2, 3, and 4 to type none, and focus on the one we did connect. Channel 1, the battery. We're just giving it a name and setting the value range from 0 to 1, as this is the range we're working with for the battery charge. While this is appropriate for batteries, other components like engine RPMs will have different ranges. By labeling our microcontroller inputs as channel 1, 2, 3, and 4, it's easy to remember that channel 1 corresponds to the first item on the panel. Moving back into the engine bay, I'm going to place breakers for the electricity. I like to do this to properly organize the power distribution. I group components like engines, transmission parts, and propulsion systems. This way, if the battery gets drained, it's much easier to identify the power draw by simply turning a breaker on and off and inspecting the power usage afterwards. The most important part here is ensuring that the batteries assigned to the motors are not being used for anything else. We're leaving the 2 front batteries for other ship-critical systems. This way, if the motors drain the other batteries, we can still power up our jets and other essential components. It's all about ensuring redundancy and reliability in our design. I've added additional breakers into the engine bay, and I'll also include breakers, relays, and power buttons in the bridge. I like to do this to prevent unnecessary battery drain when it's not needed, while also keeping everything organized. However, this is entirely up to you. Feel free to further improve upon this setup or skip it if you prefer. The choice is yours. Okay, we're ready to test. First, make sure infinite electricity is turned off. We'll be testing the throttle lever's up and down functionality from the seat, along with the button we added for powering up the bridge. Upon inspecting the motors, we can see they are producing power, and we can also confirm that the flywheels and clutches are successfully transmitting power all the way to the jets. Although everything is looking good so far, we're not moving at all. That's because our variable valves for fluid input are not open. The jets won't work without water being supplied, so let's make sure we fix that. Now, why are we doing this? Let's add a few gearboxes, and I'll explain. We want the motors and jets to run at a fixed, fuel-optimized speed. If our motors are set to run, we'll have about 110 RPS to the jets after the gearbox, and we need to control that somehow. So, instead of adjusting the power to the engine, we'll control the throttle by managing the water supply to the jets. This will help maintain efficiency and performance. To quickly assess the performance of these motors at full tilt, let's add a constant number and set it to 1. We'll connect this directly to the motors and instead route the throttle from our bridge to the variable valves. This will allow us to see how the system performs under maximum throttle. Let's power up, max the throttle, and see what we can do. If we suddenly take off like a rocket, don't blame me, it's just the jets getting a little too excited, like my mom when she hears there's cake at a party. Wow, we're skipping. This is fast indeed. It looks like our motors are more than capable. Maiden voyage, finally, success. The motors are working, and the throttle system is functioning perfectly. But remember, power without control is, well, it's like giving a toddler a loaded squirt gun, fun at first, but things can get messy really quickly. The fact is, we're running out of power quickly, and we've got no steering ability. But hey, it sure looks pretty in the water. Let's address these issues and see how we can enhance our control and power management. We'll be adding a few sensors and a function block to calculate speed in knots. Additionally, we're incorporating torque meters into the transmission system to better control everything moving forward. We'll connect it all to the instrument panel microcontroller we added earlier, but these components will also link to both the steering and engine management systems we'll be developing. Let's spawn it in again and take a look at our metrics. It seems we're overshooting our numbers quite a bit. So, here's the plan. I want the electric motors to establish our cruising speed at around 20 to 25 knots. If we need more speed, we'll kick in the jets and aim for around 60 knots while keeping fuel consumption fairly low. This strategy should give us a nice balance between efficiency and performance. So, how are we going to achieve this? First, we need a way to control our motors, and the 0 to 1 value just isn't going to cut it. We need to manage the motor's RPM more effectively, so we're adding a microcontroller to measure and set our throttle with the help of a PID controller. A PID, or proportional integral derivative controller, helps us maintain a desired set point by adjusting our output based on the error value. In simpler terms, it's like having a very attentive driving instructor making sure we stay on course, keeping everything nice and smooth. If you like what you see, have questions, or just want to share your thoughts, be sure to subscribe. I'll post a link to the ship's progress, complete with microcontrollers and all the exciting updates, so make sure you don't miss out. Your support helps me keep creating more awesome content. Looking at the motors, our target RPM was set at 8, and we're currently at 7.7. Fairly close. We'll definitely tweak the PID settings as we continue to work on this to improve our accuracy. Lastly, we're going to add a fluid jet controller. Now, I can't take credit for this. The original author on the workshop is Senjir_Vampire. It's one of my favorites, but I always tweak it a little to fit my needs. For this build, I want the steering reduction to be controlled by a speed sensor rather than the RPS. I also include a manual trim and tilt sensor input, which allows the fluid jets to autocorrect if we're rolling too much. Fluid jets are fantastic because they can redirect water up and down, giving us better maneuverability and stability in the water. Now that we've made the changes and tweaked the values, it's time to take it for a final spin in this episode. Let's see how all our hard work pays off in action. Nice steering input indeed. Remember, the only stability system we've added thus far is the anti-tilt feature on the jets. I'm very happy with this response. We'll continue to tweak all these values going forward, but for now, it's goodbye from me. Remember to subscribe, like, and drop a comment. Your feedback fuels my creativity. And if you don't subscribe, well, let's just say our ship might end up adrift, and we can't have that now, can we? In the next episode, we'll be adding the jet engines. Thanks for watching. and I'll see you all in the next one.